we have said, is analytic and can be substituted. The expressions can be complicated and so on, but they exist. You can form these expressions. Right? Okay. Now, relation with curvature and kinematic invariance. So far, we've been juggling with these variables. So somebody can say, well, maybe all these variables, and this is a criticism by referees, say, yeah, these variables are nice, but they are coordinate dependent. That means if you change coordinates, the whole magic goes away. But that's not true. I can show you that, and that's why I reply to the referees. No, no, Mr. Referee, it is not like that. So, Q scalars and their fluctuations are all expressible in terms of covariant quantities, such as psi2, the Ricci scalar, the Hubble scalar, and the eigenvalue of the shear tensor. These are all covariant quantities. In fact, they appear in the 1+3 formats. No, this is a relationship. See. The density, we already seen this, right? This we've seen. So fluctuation of the density is simply the scalar psi2. Psi2 is the eigenvalue of the electric Weil tensor, and it is also an eigenvalue of the Weil tensor itself. It is a scalar that determines the Weil tensor. It is also called the Newman-Penrose scalar for Petrov type D models. So this is an important character. So you need to get to have an appointment with this psi2. You have to wait like 6 months at least. Okay. So now this is psi2. On the other hand, we know that the quasi-local density, quasi-local density is going to be the density plus this d thing plus the density. So the quasi-local density is essentially the sum of this psi2 scalar times 1/6 of the Ricci scalar. Now, if we combine these two things, we can write the relative fluctuation, we can write it like this. It is we can write the relative fluctuations as this ratio, as this fraction, when this thing here, I think it's called bar theta, is the ratio of Weil to Ricci curvature. So the relative density fluctuation is an algebraic function of the ratio of the Weil to Ricci curvature function, because this object here describes the Weil curvature. It determines the Weil tensor. And this thing here is the Ricci scalar, which determines the Riemann curvature. So you have a simple quotient of two scalars that tells you the relationship between the Weil curvature and the Ricci curvature. This is an important feature, because what happens when this object, psi2, goes to 0? It means that all the curvature is Ricci. And it means that the models are FLRW, because for an FLRW model, the Weil tensor is 0. So this is, in a sense, this is telling you how inhomogeneous is your model. It's related to how much the curvature is of the Weil type in comparison with being of the Ricci type. See? Well, this is an interesting way of, this is one way, this is one way to this is like a valve. See, it's a valve that is telling you that the degree of homogeneity you have is proportional to the quotient of these two invariant scalars. Right?
That means if this ratio is bigger, inhomogeneity
is larger. Yes, and if it is smaller, if this ratio is 0, is no inhomogeneity.
No inhomogeneity.
If it's very small, then small. How can it be very small? if psi 2 is much, 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 much smaller than Ricci scalar,
Yeah.
then this is almost 1 and this is almost 0.
That means it's like homogeneous.
It's almost homogeneous. Almost homogeneous means that this thing has to be very small.
Small.
Perturbations or things like that, this quantity has to be very small. This quantity is not small. Now, how not small? It's maybe because notice that if this is very large and this is very large, this quantity would be of order 1. So delta is not going to be delta, no matter how big is this ratio, delta is not going to be 1 million. See, what happens if this thing gets very big, like 1,000? So you have 1,000 divided by 1,001. So this ratio is 1. It's about 1, right? If this ratio is about 1, that's lots of inhomogeneity. So that's also a very nice thing, because it's a quantity that is not going to take infinite values. Essentially, what happens is that this ratio, for over densities, this is negative. For over densities, this is negative, so the quantity here becomes infinite if it approaches 1, if this thing approaches 1, if it's negative, right? But if it's positive, the maximum value can take. Anyway, this quantity is very useful, and it's given in terms, it's invariant. If you are lost in a spaceship, you can compute these quantities for any coordinate system, right? These are coordinate independent objects. Now, what happens with the kinematic things? These are the curvature. So density is essentially related to curvature, but Hubble scalar is related to kinematics. We know that the fluctuation of the Hubble scalar is a negative of shear. So we can express this fluctuation, this relative fluctuation, in a very similar way to this one, except that now nu is the ratio of sigma to h. Sigma, what is sigma? Is the scalar that determines the shear. What is h? Is the Hubble scalar. So remember that sigma is telling you that the formation of fluid volumes. So this is essentially a ratio of anisotropic to isotropic expansion. This ratio is telling us how anisotropic is our expansion, right? So this is also a very nice interpretation for this quantity. Okay. Now, the Q-scalar fluctuation, the curvature. The curvature also we can relate to invariant quantities, but the relationship is not so easy, it's more complex. But nevertheless, either KQ or DK can also be related to these quantities in this way. It's not so easy to see it, but it can also be done. Okay, so I think we should go to tea break. Now, I'm going to ask Maple to recalculate this whole thing. And then it will recalculate the no gossips. Hey, no gossips. Want to say something, say loud, so we all know. Okay? Now, what we want to do to recalculate this Maple worksheet, we'll recalculate it, and in the end, all what we are interested is in this system. Let me do it like in this system. This is what we are interested in, this system, because this is a 1 + 3 system. We know that this system is equivalent to Einstein equations in first order, right? So after we calculate this, we define a list of variables, var's list. This is a list of all the variables that we're using. It's useful to store them. And then I'm going to ask Maple to save all these equations into a binary file. so that the next time I use maple, I don't have to redo this calculation. I simply go to the binary file and read it, and I have all the results. Okay? Okay? That understood? We're doing this? Okay? We can, in fact, also do a, it's also useful, we create a sort of a string that we are going to call info, or whatever, info LTV. And here we create a string. So it's going to be a string, 1 + 3 system for LTV models, yeah. All vars depend on T and R. This is just information, right? All variables. See? This we send that. It's just a string. Why? Because if we open this binary 3 years from now, we don't know what it is. So we just load this info file, this information instruction, and it will tell us what it is and the variables. Okay? So we save info LTV. See, we're going to tell Maple to save all these things, right? These are the information, and here.
So, how we will recall that kind of information?
I'll show you. I have not shown you yet. Obviously, I have to tell you how. Okay. And then here, another file, another thing we're going to save is the following. See, this worksheet you can get, so don't worry if you are not able. Well, we'll see how we manage, because it would be nice that you can also do this saving, the same thing I'm going to do, that you can also do. So let me just finish this. Try to copy the. Do you have the Maple worksheet, the last one?
Yes, sir.
Yeah. So please first erase everything after this, the 1 + 3 equations. Just remove the remaining, right? After these equations, put your Maple worksheet and get to these equations. Scroll down to get to this equation. Yeah, done? Now, whatever is afterwards, erase it. You remember we were not able to, I did not continue after that. That was the last thing I did, okay? So everything else, remove it. Here we're going to save the names. Okay. Have you done that? Have you removed that?
Yeah.
Yes? Yes? Remove? Now, what you are going to do is follow me carefully. Everybody, don't gossip or anything. Look at your neighbor. Look at here. Your neighbor is not going to tell you anything. Look at here, okay? Okay. Ready? Synchronize?
Yeah.
Yes? Okay. So, copy this. Select all these names, copy them, select and copy them. Go to edit and copy them. Done?
Yeah.
Done? Yes?
Yes.
Okay. Now, go to the next line, open a maple line below, Control J. Control J, you open a maple, yeah, done? Put this thing here, the string thing, it's okay?
Yes.
And then paste these names. Paste them. right? Done?
Yes.
Then close the string. Okay? Yes. Now, what you can do is, well, it's not necessary, but it's helpful. Remove the semicolon and put a comma. Put a comma. Okay? Except the last one, not the last one, but put a comma. Why are we doing this? Because we're going to save a file, and the file will tell us the names of the things that we are saving, right? Next, we do a list of variables, right? This is the list of variables. So we know the variables. And then there is an information. Try to write all this the way it is there. Okay? Why this is for? Because once we have the binary files, we read the binary files, and then we can get all this information. Okay? Okay? Tell me when you have done with all this. Tell me when you are through. Yeah? Ready? Ready?
Yes, sir.
Yeah? Ready? It's showing error if you don't execute them. Just copy them. Don't execute them. Just copy them. And if you need a carriage return, if you do enter, then it will execute them. To prevent that, do shift enter. Okay. Yeah, okay. Right. Okay, let's, now, once this is done, we're going to, the next thing you have to write is the following. See? We're going to create, let me, the next thing you have to say is instruction save, followed by the names, by the things that you are saving. What you are saving, the names, the information, the list of variables, and then each one of, see that each one of these instructions has been given a name. Each one of these equations, sorry, has a name, okay? Each one of them, okay? So you put the name of all of them, and after you put the name of all of them, you have to tell Maple where are you going to store them, right? Here I'm storing it in this direction, but this is my direction. That's in my system. You have a system, a hierarchy of files. You tell Maple where do you want it stored, right?
Sir, in my computer when I use it assignment operator, it is not coming with the red sign.
What?
I have used
Select the color. First select the color.
You have this horrible, stupid document form.
Oh yeah, I'm sorry, I started in document.
No, don't do that. Don't do that. That's terrible. To do that, it's Control M. Control M will give you this. I don't know. I don't want to touch it. But Control M. But then you have every time you sorry, every time you have to input a line, do Control M.
Okay, I will just copy it in.
Yes.
Worksheet.
Look, I'm going to go now because otherwise we won't have time. You get this thing, you do it on your own in calm, okay? So otherwise we don't have time to do it. It's already 12. Okay? So what we do now is to execute, to ask Maple to execute the whole thing. Has people already copied this? Yes? Okay. So let's go up, and then we put the cursor here, and we tell Maple to execute the worksheet. Okay? It's going to execute it. So, right? And so now Maple should have placed in this directory. Well, we should also check that Maple didn't have any error. Check that there are no errors. Check that there are no errors, that it executed everything. There are lots of things that we're not saving because we're not interested in the intermediate steps. We just want to save the final thing. All sorts of things we're not saving. Yeah, well, that's okay. All these things were, there are no errors, no errors, no errors. Maple is saving everything, everything. Right, everything, everything. Shear constraint, everything. W constraint, etc., etc. Okay, so Maple should have saved a file called ltvsystem.m in the directory I asked it to do. So let's see if Maple did that. Here it is. Here you can see the file that Maple has saved. Now this is a binary file. It has all junk. Don't try to open it because we don't need to open it. What we need is to ask Maple to read it. Okay? So now we open a fresh new worksheet. See, open. New in worksheet mode. Please don't enter document mode. Document mode, shit. Total crap. Right? Now, this is going to appear on title. Let me save this thing. It's going to appear on title. Okay. Now, there is one way. You can already save it. Once you open it, you can save it and give it a name. Give it like I don't know, the 1 plus 3 system. Okay, or we can call it LTV 1 plus 3. No, I don't know if it will accept this. Okay, system. LTV system, something like that. Now, here, if you go to in Windows, it might be different. But for example, if you go to format, I think it's format, and you go to, there is one way to tell Maple to write it. See, Maple input. You can always change whatever, see, I have configured my computer so that it automatically enters in red. If you, there is one way to configure your computer, but I don't know how it is in Windows. But it doesn't matter. If you do Control M, automatically will put the cursor in the right way. But then you have to do, every time you type an instruction, you have to do that, okay? Because it is very important, the computer environment, that you can distinguish input and output. Now, in the Maple company, in order they have this idea people in English-speaking countries are sick. Not everybody, but a lot of people are sick. They are so afraid of the complaints. It's like they are so afraid that somebody will complain and start crying, say this is not friendly, blah, blah, blah. That they make such big efforts to make things so friendly that then the things become dysfunctional. See, they have modified the input section so that it looks so beautiful that it's undistinguishable from the output. And this creates a lot of confusion. And this making things so comfortable means that people become mentally lazy. It's like somebody who at least has to stand up and change the channel of the television. But then they complain, nah, that's too much work. Nah, too much work. Then Canada, typical idiotic and English-speaking country, no Canadian here, okay. Typical idiotic English-speaking country say, no, we invent TV control. So you are here, drinking your beer, very comfortable. What's the end product? The end product is a person say, hey, something is wrong here, I have to wake up, I have to stand up and fix. You see? It's the same thing happens with a computer. They try to make it so comfortable that it is dysfunctional. So we have to fight that. So no forbidden document environment, total, absolute dysfunctional. Don't use it. Okay? So restart, always good idea to write restart, right? Because if things go bad, you go up and clear everything. Okay? Now, we will need to we will need to read defalias. We will need the defalias file. Right? You already have it, right? So the instruction is to read it. First instruction is to read the defalias file, which of course I have it, this is my direction, my path. You will have a different one, right? But you have to, don't execute things so far. Let's first add a few. Now, the same read statement will be applied, but instead of defalias, to the system that you create. The same, right? The same, exactly the same statement. Don't execute anything yet, okay? So it is going to, the same thing, but to the file that we created that was called ltvsystem.m. So we copy, and here, instead of defalias, we write ltvsystem.m, right? Okay? Everybody there? Everybody there?
I have one question that you have given that read command and you are telling that from computer to computer it is different and you can choose according to your own way.
Yes,
Yeah.
yes.
But so from where we have to choose from computers? Means we have
Depends on your system.
same system, no? Yeah.
Depends on your system. Like, see, the Mac is Unix, so this is a Unix. This is a Unix syntaxis for directories,
Okay.
for files, right? But if you are in Windows, I think you have to use the backslash, that's right. I don't know, not familiar. But depends on the system of the person. Now we can already execute these things. It will say, will restart, then Maple will read the falias, and it will read the other system, right? So we can put a comment here saying we load the falias and the binary file. Okay, we've loaded, right? So now, once we have done that, see, this is what we have saved, right? So let's see. This, we have saved these things. We assigned these names to certain objects. So let's see if Maple recognizes them. Okay. Yeah. It does. So this is what we have saved. See, we have saved Raichaduri, energy conservation, shear propagation, W propagation, shear constraints, W constraint. Okay. And we have saved this information, and we know we have these variables. Okay. I don't know why it didn't write mu, but it's interesting how mu was mu declared. Let me write something. Ah, I think I spotted an error. We're not using mu, but rho. So, well, the variables, the declaration of variables, instead of rho, we should use instead of mu. Well, that's a trivial error. But in case you find this error, you find an error, that's easy to arrange. You correct the error, right? And you ask Maple to redo the whole worksheet.
Restart.
Yeah, you go up on top and you tell Maple, edit, execute worksheet, right? And it will generate another file on top of the one, right? It will generate the other file that will be corrected, right? Then, once you do that, then restart, you read the falias, and you read the other file, and here. This is the variables we have. So what's next is to declare these variables with the falias, right? Okay? Declare variables in the falias. Okay, so we do the falias. Okay, the variables depend on PR, and the names of the variables are what? Theta, rho, y, psi 2, and sigma. Okay, these are the variables that. See, what happens if you say? See, when you say this, see, we have been omitting. We have putting colon instead of semicolon. If you write semicolon, Maple is telling you that it's already considering these variables to be functions of the variables you declare and writing all their derivatives up to third order with subindices. Okay? Okay? So, now, be careful here. Once you do a de Faglia statement, you shouldn't do it again, because it will confuse Maple, right? Because Maple is going to think that each one of these symbols is a function of this coordinate. So be careful. If you need to re-execute de Faglias, then go on top and restart everything. Okay? This is an important advice. Okay? Execute only once. If need to re-execute, go to top and rerun worksheet. Okay? So suppose we had an error, we need to re-execute it. We go to the top, we re-execute everything, and then we execute this thing again. Okay? Well, now, next thing, we are going to take the names. See, we copy this here. Here we have the names, and we should get the equations. And once we get them, we are ready to use them. Okay. That's it, we have them. Okay. Now we can work with them. So, now we can work with them. Okay. First thing we are going to do is to change instead of theta, we are going to work with h, right? Remember, h is theta divided by 3, right? So that's a very simple thing to do. See? First, we replace theta by h. So this is we define the substitution. So say this is the equation that relates theta with h. And the thing, no. First, we have to declare h. We have to tell Maple that h is a new function. So de Faglias, dr, and h. Okay. And then, every time Maple sees theta, it's we're going to ask Maple to replace it with 3h. Okay. So this will have to be substituted in all the equations, right? Now, we say eval subs, okay, equation theta h in the first equation, right? We want to substitute this in the first equation, which is Raichaduri, right? Right? So we notice that there is a minus, there is a 3 there, right? Bothering, okay? So what we can say, we can, for example, at this point say ht is going to be solve the equation, because what we want is to solve the equation for ht, right? It's a simple equation, right? Solve above with respect to ht, right? And that's it. This is the first equation, okay? And so let's call this, instead of Raichaduri, let's call this equation ht, right? This is the equation for ht, okay? So we do that in the next equation. The next equation is E cons. Do the same thing in E cons. Say, if I'll substitute this thing, but in E cons, in E cons, okay? We get this, and then we do the same thing. We ask Maple to solve for rho t, this is rho t. That's it. That's the second equation. So let's call this ec rho t. Okay? Very simple. Just substituting. And the next one is shear propagation. Okay. Shear propagation. Okay, we do the same thing. Eval this thing, shear propagation. And here what we say is do exactly the same. Sigma t, solve above 1 sigma t. And this is the equation sigma t. And we still need to do this in several, in the equation in W prop. It's a bit mechanical, this thing, but I'll substitute this here. Okay, and then psi 2t equals same thing as here. Okay, and simple. Okay, so this is the equation. Still need to substitute in the constraints, in the shear constraint, and in the W constraint. Same thing, eval subs here. Okay. In this one we can, let's leave the, let's leave this one the way it is, without, because it doesn't matter. We can, let's leave it like this. Let's call it SH equals to 2. And then we do the same thing for W constraint, and we're done. Same thing for W constraint. We call it W constraint number 2. In fact, this didn't change. So, it's always good to write a summary. Summary. Now the syntaxis is easier because we have instead we have this system to call the equations, so it's easier to remember them. Okay. Okay, very easy to remember them. these are our equations now. These are our equations. But now we've passed them, we've written them as evolution equations, right? These are evolution equations. So what's the next task? The next task is to substitute the Q scalars and the fluctuations on them, right? So we put all this information we've derived now. So that means we will have to introduce, let's work now with rho Q and HQ, not with the omegas, with rho Q and HQ, see? So we have to introduce this variable, see? So let's, in fact, it's also useful to do some writing here. So, Q scalars and their fluctuations. Yeah. So, how do we do that? Well, we know that, for example, we know that, for example, and here I can use maple typesetting, which is very nice. Don't worry if you cannot follow me. You can do that carefully later. See, I dial here, I push this button, math, and then I use, for example, see, here is rho. I say rho will be equal to rho Q, rho Q times D, just to simplify, okay, right? And then the same with H, say H will be equal to HQ plus DH, okay, right? So I have to input the DH and right, and okay, H, and also what we will need is the formula for DH. We need, for example, to say that D D rho is equal to or rather let's write it like this better. Let's say something like rho Q prime will be equal to 3. Remember that here big R is being, Y is big R, right? So I did not want to use big R to avoid conflicts with a Riemann tensor, right? So we use the same notation. Same thing here. H prime Q is really equal to 3 Y prime divided by Y times D H. Okay. And remember that rho Q, okay, so we have these things, we have to introduce them. So first we are going to introduce rho Q and HQ, right? If alias. These are functions that depend on R, and we are going to call them rho Q, HQ, D rho, In fact, there is one simple way for example, I use sometimes this notation. See, because it's easier, the symbols are smaller. Of course, you have to explain very well that MQ is rho Q, right? Okay. Also, there is another thing we have to explain that we will have to use is that psi 2 also has psi 2. We have to input this information. Psi 2 is at one point we need to input this information for pi 3 Okay, so here the convention will be, see, we can say this, okay, rho Q will be MQ, right? And D rho. Now, better write this thing. Anyway, you can write it like this. You know, it's because once you put these characters, Maple doesn't read it, so you can write whatever you want. D rho equals dm. Okay. We're going to use this convention. In fact, you can change the color of this very easily so that Maple does not get confused. You can change this color here. So, right? Ready? Go. It's defined. Now we have to make all the substitutions. For example, we work first, the simplest equation is ik rot. See? We say eval, well, we can say something like this. Ek rho, equation of rho will be rho equals mq plus dm, right? And then we also have an equation for h, which will be h equals hq times dh, okay? Right. We're going to insert these equations now, okay? So, first eval SOX equation for rho, an equation for h in the first ek here. So notice that now we have we will have to work out algebraically this equation. This is the first case. Now, once we substitute in the others, we will get equations for NQ and DM that we will also have to work with, okay? So let's call this one equation 1. Okay, equation 1, okay? Now let's substitute in the equation in the Recalculating equation. Okay? And let's call this equation 2. Okay. Now let's substitute in the shear equation. But see, the shear, we already know that the shear is minus dH, and W is 4/3 of phi d rho. So we can also substitute these things, right? But meanwhile, if you want, we can we can substitute in sigma t. What happens when we substitute sigma t? Let's call this equation 3. And then let's call equation 4 when we substitute this in psi 2. Okay. Okay, so and let's substitute also on the constraints. Let's substitute in the first constraint here. You follow me, right? It's just substituting. It's donkey's work. Okay, say egg4. Oh, sorry. This duplicate name. So egg3 and egg4. Now this is going to be egg5. Oh, tonto. Okay. So, and egg6. So now let's summarize all what we have. Summary. The summary now is very simple because it's egg1, egg2, egg3, egg4, egg5, egg6. Okay, this is what we have. Oh, egg. Egg. So this is what we have. Now we now have to tell Maple that sigma is the negative of dH, and so otherwise we have this sigma and we have psi 2, but we can also eliminate those quantities in terms of the flow of the new variable. So let's do that. See. Next information is. Next, we substitute sigma equals minus dh and psi 2 equals kappa. Okay. In half an hour we finish. Okay. Okay. 6 minus. Now, why kappa by 6? Because remember that kappa is shorthand for 8 pi. 8 pi g divided by c squared. So if we want 4/3, then we have to divide by 3. Remember that we take c and g equal to 1. So if we want 4 pi by 3, we need to divide 8 pi by 6, right? That's why. So we make this substitution. So say for ec sig ec sigma will be telling Maple that sigma is to be substituted by minus dh, right? And ec psi 2, we're telling Maple that psi 2 is going to be substituted by kappa minus kappa divided by 6 times dm. Okay? So now we substitute these things, but notice that this, we don't have to substitute them everywhere. Well, actually, yeah, because the only equation we don't need to substitute anything is the first one, ec1. But in all the other equations, we have to make the substitution. So to be on the safe side, we substitute everywhere, right? Okay? And since we have to do donkey's work mechanically, we might as well do it in a single instruction rather than going one by one. So we're going to say to do the following. See, look. I do this by return carriage. Return carriage. Okay. So I'm going to call equation 1 will be eval substitute the equation for sigma, the equation for psi 2 in equation 1, right? Bye. And we're going to do the same for all of them, right? Except we change the number, right? In equation 2, right? We can even erase all this and yeah. Okay. Equation 3 in 3. Equation 4 in 4, and equation 5 in 5, and equation 6 in 6. Okay?
Yeah, we still have to change the 2 to it.
What?
Equation 2 in 2.
So everything correct? Everything okay?
Yes.
So here they are. Now let's look at the last equations, because here, there is something. There's something I don't like here. Well, notice that we have, let's look at the first four equations. First 4 equations, we have 4 variables, 4 derivatives. MQ dm, HQ dh, and they are all distributed. But notice that there are no more equations there, therefore it's an algebraic system. So 4 equations for 4 unknowns. See? The unknowns are the derivatives, the dmt, the dht, the mq, and so on. So we can solve this system algebraically. and we can isolate the equations for MQ, DM, HQ, and DH. So we can work already with this form, right? So this would be the point here. There is anyway, I'll work out. So make a comment here. Comment. We work with the first 4 equations. Okay, right? 4 equations for 4 derivatives of t. Okay, so it's very easy to say solve the set formed by equation 1, equation 2, equation 3, equation 4, and the variables that we want to solve it for are MQT, right, HQT, right, DMT, and DHT. Right. So these are our equations. These are equations for, see, the first one equation here for, this is an equation for DH, right? This is an equation for DM, and then this is the equation for HQ of T, which is DM, DH. There is something. So let's write them up. Let's write them up. Let's call this sol. So let's see, sol 1, the first one. DH of T. And sol 2, sol 3, sol 4. There is something fishy about this. Probably made an error, but meanwhile, the point here is to illustrate to you how we change the system, right? Now, let's look now, for the time being, these are self-consistent equations. It's a system that can be solved numerically. However, we have to look at the constraints. Let's look at equation 5, right? Now, what is the definition? We have to substitute here. We have to substitute the definition of the constraints, the definition of the fluctuation. See? Okay, here. What we need to do is substitute this formula here, these things here. We have to substitute this two. We have to substitute this two in the constraints. Now, here we have equation 5, but we have to substitute, let's say eval, substitute, and then HQR, what is the formula for HQR? Equals 3 times YR divided by Y, all this multiplying DH, right? Okay? And we have to substitute this in equation 5. So it's automatically satisfied. The constraint is automatically satisfied. We don't need the constraint anymore. In fact, the constraint itself is simply the definition of the fluctuation. Right? So let's do the same for 6. 6 is this. Now here we substitute mu r, do the same thing. Let me see. I think I understand why there is. Let me just check something quickly. Yeah, I think I see there is an error here. I can see the error now. Side 2. Yeah, I think I can see the error. Yeah. Okay, I'll fix that. But meanwhile, we do the same thing here. But I'll substitute mk equals dm, but this is substituted in 6, right?
So mu r. So there is mu r.
Yeah, that's a problem. It did not. Yes, that's a
Rho
problem.
r. Rho r.
It's mu. That's why it failed. Yeah. Yeah. Exactly. Exactly. That's the problem. It has a mu. So let's first replace the mu with r. Okay. And try mu r equals. Yeah, that was an error. Makes it. Yeah. So first, we make this correction, and then we substitute here, but it's still, yes, it's, once we substitute, this screwed up the whole thing. So we have to do more substitutions. It's going to be easier to fix the thing from the beginning. But I'll do that, don't worry. So what we're going to do here is eval substitute rho, that was, I think we call it ec rho. Go, okay. Have to do these substitutions. First, this one, then this one, then this one, and then we expand everything. 0. Yeah, so that was an unfortunate mistake. So this constraint is also satisfied. So we are left with these equations, and we have to. Thing is, yeah, these equations are. There is something. Yes. These equations are still not complete. Why? Because there are relations between DH and DM. There are relations between DH and DM. The ones I've written before, right? We also have to apply these constraints. So, but at least now the constraints, the equation 5 and 6 are automatically satisfied, okay? Right? So we don't have to worry about them. we have only to worry about the evolution equations. I don't know if you realize how fantastic this is, because the constraints were differential equations. With our choice of variables, they are automatically satisfied. So we don't have to worry about them. We can only look at the time equations. So let's look at the time equation. So let's call this EE1 is solution 1, EE2 solution 2, EE3 solution 3, EE4 solution 4, right? So we check the constraints. See? Both constraints, say a comment here, check constraints. Okay. They are satisfied identically. Fantastic. Okay. Satisfied identically. So let's look at these other equations. See? So let's look at evolution equations. Evolution equations are EE1, EE2, EE3, EE4. These are equations. So we still need to work them, to work with them. Okay, first, we have an equation that says DH, but it will introduce curvature. Let me see if that's okay. What I don't like is DHQ. Yeah. We have this equation DH 2HQ times DH. I'm just going to write it. It was 8 pi. 8 pi is kappa. Kappa by 3. This is kappa divided by 3 times dm minus, I have not defined it, but let's call it dk. So we have this variable, this 2 times. I have this thing here, so we can eliminate dh. dh equals solving dh. Now we substitute this. Substitute this. Say the in. Let's see EE3. EE3. And we also have to substitute HQ. HQ is correct. Just this dm. Okay. Expand. This is the only equation that is not correct, but I have to look at this carefully. Now, there must be an error that I made because the equation is not coming correct. Okay. But I'll do that. I'll do that carefully. I think we should. I'm going to stop here. The point was to show you how we can replace it. See, from a mathematical point of view, the important thing is that the constraints are automatically satisfied. Therefore, what you have is a system of evolution equations. See? Okay, this system that I wrote here has an error. There is the right equations are not those. So there is an error that is probably related to the original 1 plus 3 system. Maybe a sign error or something like that. But the first two are correct. The equations, see? But this equation, the term that is, these two terms are, they shouldn't be here. This term and this term, they shouldn't be here. The equation would be only these two, which is identical to the FLRW Raychaudhuri equation. Right. And this one here, this term should not appear here, right? But I'll correct that. This is probably error signs or whatever. But the point I want you to see is how these variables, the magic of these variables, is constraints are satisfied. Therefore, evolution is simply satisfy. These equations are only derivatives of time. There are no constraints. Constraints are satisfied, right? So the constraints are only necessary at the initial time. You satisfy them, and then that's it. The system propagates by these equations. And this is a system of differential equations that can be easily solved with Maple or Mathematica. And we can complement this system with two extra equations that will also determine the metric functions. Because, see, let me just, with this I finish. These are the variables we have now. Our variables are this. Our variables are HQ, rho Q, DH, and D rho. Okay? So these are our variables. Okay? However, we know something. We know, for example, that HQ is A dot A, right? We also know that DH is gamma dot 3 gamma. Okay? We've seen that previously. Okay? You can check that out also. So we can add this equation can add these two equations to the system. And then when you solve the system, it will also give you A and gamma, which are the metric functions, numerically. No Friedman equation, no Big Bang time, and all this is built. The initial conditions to work this system. See, the initial conditions are going to be rho Q0 and HQ0. That's all you need, right? Because how do you find this? Well, very easy. No. And then you have, and also initial condition. This is your set of initial conditions. And then the system is propagated, right? Okay? This is how you do it numerically. Now, of course, to do it numerically, it's useful to make the variables dimensionless and so on, requires certain tricks and so on. But theoretic, conceptually, this is what you do. You have these variables. algebraic constraints are 0. In fact, your algebraic constraints are being satisfied by this is the form of the algebraic constraints in the initial slides. It's essentially the algebraic constraints are the definitions of the fluctuations. Right. Now, when I started working with these variables, I didn't set myself the idea, take the constraints and use them as definitions. No, it just happened. Right. A little bit of these variables was trial and error, not necessarily that I had a plan or whatever. Okay, but that's it. We can now look at the dynamics of the models in terms of these variables. Okay. Now what I'm going to do for tomorrow is to correct this thing, because there is an error, sign error. Let's see, maybe there is a mu somewhere. Is there a mu? No. Now there are three terms that shouldn't be there, and normally when terms like this happen, it's because of an error sign. Probably the shear propagation equation, or there is an error sign there, so I'll check that. But otherwise, it has to happen like this. Okay, so see you tomorrow. Okay.
So tomorrow in theory class, we are going to teach about.
Tomorrow is the exam, right?
Today.
Yes.
It was today? No. Tomorrow.